Hello everyone, welcome back to ZypherSpaceCore. In today's episode, we are going to study linear feedback shift register, commonly called LFSR. LFSR are one of the most foundational concepts behind pseudo-random sequence generation and the stream cipher design. They are widely used in communication systems, cryptography, digital electronics, and wireless technologies. Before understanding how LFSR works, let us first understand why they are important. LFSR plays a major role in generating binary sequences that appear random. These random-looking sequences are useful in encryption, synchronization, communication systems, and hardware testing. One important point is that LFSR connects simple mathematics with real engineering systems. Even though the structure is mathematically simple, the applications are extremely practical. Now let us look at real-world uses. GSM mobile encryption systems such as A5 bar 1 used in multiple LFSR internally for the stream cipher generation. Bluetooth communication system also uses pseudo-random techniques for frequency hopping and synchronization. Satellite communication systems are sequence generation for reliable data transmission. Error correction codes and CRC generation heavily relies on LFSR structures. In digital hardware testing, LFSR generates pseudo-random test patterns for checking circuits. Radar and sonar also uses special sequence generating using principle related to the LFSR. This application shows that LFSRs are not just theoretical idea, they are used in real technologies. From an educational perspective, the LFSR help us understanding the sequence generation, feedback mechanism, and the role of linear algebra in cryptography. They all also help us understanding the transition from simple digital logic to advanced stream cipher design. Another very important point is understanding why linear architecture become very weak in cryptography. A single LFSR is fast and efficient, but because its behavior is linear and deterministic, the attacker can mathematically predict the future output even if bits are observed. This limitation motivates the developers to develop the strong stream cipher that combines multiple LFSRs with a non-linear operation. To understand LFSR, we first need to understand shift register. A shift register is a collection of flip-flops connected together to store binary values. Each flip-flop stores exactly one bit, either 0 or 1. When a clock pulse occurs, all the stored bit moves one position either to the left or to the right. This movement is called shifting. Now let us observe 4-bit example. Initially the register contains 1011. So the current state is 1011. During every clock cycle, all bits shift towards the right side. The rightmost bit becomes the output. At same time, no bit can enter into the left side. After first clock pulse, all the bit moves one position. After another clock pulse, the process repeats again. Eventually, the original bit leaves the register completely. Now let us understand why shift registers are important. The hardware is extremely simple because only the flip-flops and connections are required. This operation is very fast since the shifting can happen directly in the hardware circuit. So the power consumption is also low, making them useful for embedded and their communication system. They are very easy to implement in silicon chips. Another important property is the deterministic behavior. If the same initial state is used, the same sequence will always be generated again. This reproducibility is very useful in testing and synchronizing systems. Now let us study the main component that forms an LFSR. The first component is the shift register itself. The multiple flip-flops are connected in cascade, meaning the output of one flip-flop becomes the input of next one. Each flip-flop stores one bit. If there are n flip-flops, then the register stores n bits in total. The second component is the feedback function itself. This is the heart of LFSR. Selected bits from the registers are combined using XOR gates. The XOR results become the new input bit inserted into the register. Because XOR is a linear operation, the entire structure is called a linear feedback shift register. Next we have tape. Tape are specific bit positions selected for the feedback calculation. Different type positions generate different output sequence and determine the mathematical behavior of LFSR. Another important concept is the initial state, also called the seed. This is the starting binary value loaded into the register before the operation begins. The seed must never be all zero. If every bit becomes zero, the XOR feedback also remains zero forever, and the sequence permanently dies. Finally, the code signal synchronizes the entire operation. On every code flush, the bit shift feedback is calculated and a new bit enters the register. Now look at the architecture diagram. We can clearly define the flip-flop, the tap connection, the XOR feedback logic, the clock, and the output path. Together, this component form the LFSR architecture. Now let us study the important properties of LFSR. First property is pseudo-randomness. The generated sequence appears random even though the system itself is deterministic. If the same seed and the same polynomial are used again, the exact same sequence will be reproduced. Second property is efficiency. The LFSR requires only shifting operation and XOR gates. Because of this, they are extremely fast in hardware and consume very little power. This makes them suitable for real-time communication system and embedded devices. The third property is periodicity. Eventually, the sequence repeats after a certain number of bits. For an n-bit LFSR, the maximum possible period is 2 raised to n minus 1. The exact period depends upon the feedback polynomial and the initial seed. The fourth property is predictability. If an attacker knows the current state and the feedback polynomial, the future output can be predicted mathematically. This predictability is the major weakness of single LFSR in cryptography. Now let us understand feedback in LFSR. Feedback is a mechanism that allows an LFSR to continuously generate long sequences. Without feedback, the bit would eventually disappear completely from the register. The process begins with correct state, register state, and current certain position called the states are selected. Selected bits are XORed together. The XOR result becomes the new input bit inserted into the register. Now let us examine with the example. The current state is 1011. Selected states are bit 3 and bit 0. Bit 3 contain 1, bit 0 contain 1. Now XOR operation, that is 1 XOR 1 equals 0. So the feedback bit becomes 0. After shifting left and inserting 0, the new register state becomes 0101. Now let us understand the important properties of XOR. XOR is a linear operation. It is extremely fast in hardware because only a single XOR gates are required. It is deterministic, meaning the same input always produces same output. The another important property is reversibility. A XOR A equals 0. XOR is also commutative. A XOR B equals B XOR A. And associative. The grouping of operation does not change the final result. Because of these properties, XOR is widely used in cryptography and digital logic and communication systems. Now let us study a complete step-by-step working example of a 4-bit LFSR. Here the feedback polynomial used is x raised to 4 plus x plus 1. This corresponds to tape at the position 4 and the 1. The initial seed is 1101. The shifting direction is towards the left. Now let us follow the sequence cycle by cycle. Initially the register state is 1101. The output bit is rightmost bit S0, which is 1. Now calculate the feedback using S3 XOR S0. 1 XOR 1 equals 0. After shifting left and inserting 0, the next state becomes 0, 1, 1, 0. Now move to next cycle. The current state is 0, 1, 1, 0. Output bit 0. Feedback 0 XOR 0 equals 0. Inserting 0 after shifting. The next state becomes 0, 0, 1, 1. The next cycle, the current state is 0, 0, 1, 1. Then 0 XOR 1 equals 1. Then insert 1. The next state becomes 1, 0, 0, 1. This process continuously repeated. Eventually, the previously generated state begin appear again. At that point, The sequence starts repeating the forming the period of LFSR. This demonstrates how a very small register can generate a long binary sequence. We talk about characteristic polynomial. The mathematical behavior of an LFSR is described using a characteristic polynomial. This polynomial defines which position are tapped for the feedback generation. The general formula is P of x is x raised to n plus etc. to x raised to k etc. to plus 1. Now consider the example, that is x raised to 4 plus x plus 1. This means there is a tap position at the position 4 and there is another tap at position 1, and the constant 1 is always included. The position missing from the polynomial are not tapped. Now let us consider some few examples. For a 4-bit LFSR, that is x raised to 4 plus x plus 1, there is tap position at the bit 4 and the bit 1. And for 8-bit LFSR, polynomial will be x raised to 8 plus x raised to 4 plus x raised to 3 plus x plus 1. For 16-bit LFSR, x raised to 16 plus x raised to 5 plus x raised to 3 plus x plus 1. These are some examples for the n-bit LFSRs. As the polynomial degree increases, the sequence complexity and possible circuit length also increases. Now let us understand the difference between the primitive and non-primitive polynomials. A primitive polynomial generates a maximum length sequence. For an n-bit LFSR, the maximum possible period is 2 raised to n minus 1. In the 4-bit example, 2 raised to 4 minus 1 equals to 50. The polynomial x raised to 4 plus x plus 1 is primitive. This means the LFSR can visit all 15 non-zero states before repeating. This produces better pseudo-random behavior and the maximum utility of the registers. Now compare this with non-primitive polynomial. If the polynomial x raised to 4 plus x raised to 3 plus x produces only period of 7, many possible states are never revisited. The sequence repeat much earlier. This wastes registers capacity and reduces randomness quality. Because of this, primitive polynomials are preferred in cryptography and communication applications. Then next we talk about maximal length sequence. A maximal length sequence, also called an M sequence, is the longest possible sequence generated before repetition occurs. This happens only when a primitive polynomial is used. For an n-bit LFSR, the maximum period length is 2 raised to n minus 1. The reason of subtracting 1 is the all zero state is excluded. For example, 3-bit LFSR can generate maximum period of 7 bits. A 4-bit LFSR can generate a 15-bit. 8-bit LFSR can generate 255 bits, and 16-bit LFSR can generate 65535 bits. And 30-bit LFSR can approximately 4 billion before repeating. One most important property of M sequence is that all possible non-zero states are revisited exactly once. That all zero states must always be avoided. If the registers become all zero, the feedback remains zero forever and the sequence permanently stops. The maximal length sequence provides long period, efficient state utilization, and good pseudo-random characteristics. Now let us study the statistical property of LFSR output sequence. The first property is the balance property. In a maximal length sequence, the number of zeros and ones is almost equal. For example, in a 15-bit sequence, there may be 8 zeros, 7 and 7 zeros. 8 ones and 7 zeros. This near balance makes the sequence resemble random pattern. A run means a sequence identical, consecutive identical bits. Example, includes 1 1 1 0 or 0 0 0. Short run occurs more frequently than long run. This resembles the behavior of true random sequence. The third property is autocorrelation. If the sequence is shifted and combined with itself, the similarity becomes very low except at zero shift. At zero shift, the sequence perfectly matches itself. Low correlation is extremely useful in communication, synchronization, radar, sonar, and spread spectrum technologies. Together, these properties make LFSR sequence behavior similar to the random sequence, even though they are generated deterministically. So today, we studied shift registers, LFSR architecture, feedback mechanisms, polynomials, and statistical properties of LFSR output. In the next episode, we will look into more LFSR examples and explore how the multiple LFSR are combined to build strong string cipher systems. Thanks.